In this question, we're asked to calculate the increase in potential energy, or to prove that the increase in potential energy is given by the expression over here. Now, we're going to need to use some of the skills that we've learned or picked up along the way in order to help us calculate this. So the best place to start with is to sort of look at the potential energy, gravitational potential energy, right? And that's mass times gravity times the increase or decrease in height. Okay? And we have the mass and we know the gravitational constant, so the only thing we don't know is the height. Now, using a bit of backwards thinking, we can actually get there. Now, the height that we're interested in getting is this height over here. Okay? We are interested in the total vertical change, not the total height that we've increased along the slope, but rather the increase in vertical height that the object has risen. So, looking at this problem, and given the information that we are given, we know that this angle is some angle theta, and with a bit of simple geometry we can also prove that this is also an angle of theta. And considering the information we're given, if we were able to calculate the distance that the object had moved up the slope, so that's this distance over here, using some basic trigonometry we'd be able to calculate the vertical height that we've increased. Now, in order to calculate that displacement, we can consider the information we're given. We've given an initial velocity. We know that the final velocity is going to be 0. We want to calculate the displacement, and so we need one other component. And the other component that we're going to be interested in is the acceleration. Now, the acceleration of the object we can calculate using Newton's second law. Right? So, using Newton's second law, where the net force is equal to mass times acceleration, we can actually calculate that acceleration. And we can think about it as a deceleration because the object's going to be slowing down. Now, in order to calculate the net force, we're going to have to consider all the forces on the object. We're going to have to resolve them both vertically and horizontally, and resolve in the direction of motion. So the first thing we want to say is the direction of motion is going to be up the hill. Okay, that's the direction the object is moving. And let us consider all the forces that we know. Okay, we know that the object has some weight component of mass m, so it has a weight force of mg. We also know that there's friction. Friction always acts in the opposite to the direction of motion, so we're going to have a friction component in this direction, which is the coefficient of friction multiplied by the normal contact force. That obviously means that we have a normal contact force going perpendicular to the slope. And obviously, as stated, we've got the angle as theta. So we have multiple forces, right? The weight force can further be broken down into its two components. So we're going to have the force perpendicular to the direction of motion, and we'll have another component in the direction of motion. Okay, remembering that this angle inside here is also theta. So the first thing we need to do is resolve perpendicular to the direction of motion. So in other words, we're going to resolve in this direction first. Right? There's no acceleration in this direction because it's not in the direction of motion, it's perpendicular. So our forces are going to be equal, right? And the only two forces acting in the perpendicular direction are going to be the normal contact force and this component of the weight force, which is really nice because we can immediately then find our normal contact force. It must be equal to that weight component, right? That weight component is going to be the force, mg, right? That happens to be the adjacent side, so cos, and the angle is theta degrees. From here, we're now able to calculate our friction force. So our friction force is equal to the coefficient of friction, which was given to us as mu, and we've just calculated the normal contact force is mg cos theta. Right, now that we've calculated the friction force, the only other force that we need to consider in the direction of motion, well, against the direction of motion actually, is this weight force over here. Right. We can quickly just summarize that as going to be mg, that is the opposite sides of sine theta. Right, now we're ready to find the net force. Okay, so using Newton's second law, where force is equal to mass times acceleration, where this force here is our net force in the direction of motion. So we're not interested in any of the perpendicular forces anymore. We've resolved those. We're just interested in the forces in the direction of motion. And these are the forces that are acting in this direction. Right, both the forces are acting against the direction of motion, right? So they will be both negative. So the friction force was mg cos theta, and the other force is mg sine theta. These must be equal to mass times acceleration. The mass of the object is m, and the acceleration is the thing that we're trying to work out. Okay, every term includes an m, and so we can just divide through by m, and that finally gives us our acceleration as negative mu g cos theta minus g sine theta. Now we have our acceleration. From here, we're actually able to calculate our displacement. So let's take a look at the information we have. We know the initial velocity is equal to, if we go back to the question, v. Our final velocity is going to be 0. Our acceleration is equal to, well, it's equal to this that we've just worked out. Minus mu g cos theta minus g sine theta. And using one of our equations of constant acceleration, we can actually calculate the displacement. And the displacement is this displacement here that we're trying to calculate. Right? How far up the slope the object has moved. Right, v squared is 0. U squared is v squared 2 times the acceleration. So this is that negative mu g cos theta minus g sine theta displacement. Right, we'd like to solve for displacement here. So these are both negative terms. We can multiply through by 2 if we wanted to. They're both going to be negative. But the easiest thing to do is just to move all of that over to the other side. And then we'll divide through to solve for displacement. These are going to become positive, obviously, because we've actually moved them over. So now we have our displacement. Okay. Now let's go back and have a look at what we need. Right, we've actually calculated the total displacement that this object has moved up the hill. So we've calculated this distance here. That happens to be the hypotenuse of this triangle over here. We're interested in finding the opposite side of that triangle. Right, opposite over hypotenuse is sine, and the angle is theta. So we can say sine theta is equal to h, which is the unknown that we're trying to solve, over hypotenuse, which is the displacement that we calculated previously. So h over, and here we have v squared over u cos g cos theta plus g sine theta. Right, because we're trying to solve for h, we can just multiply the entire denominator onto the other side, and that will give us h equal to sine theta v squared, which is probably going to be better if we put in the front, all over u g cos theta plus g sine theta. So we finally have the height of this object. From here we can actually finally work out our potential energy, okay, which is mass times gravity times height. So we have mass times gravity, and we're going to multiply that by everything we've just calculated. So we have v squared sine theta all over mu g cos theta plus g sine theta. Now we could factor out g from both those terms, and they will also then end up cancelling with the g on the numerator. And so we're just left with v squared m sine theta all over mu cos theta plus sine theta. So if we go back and have a look at the way it's written, have I forgotten to carry over my 2? So we can just go back and remember that there are supposed to be 2's here. If we go back and have a look at the question, everything is expressed as tan. And we have sines and cos, right? So what's happened here is we've basically said, let's take v squared mv squared sine theta over 2 mu cos theta plus sine theta, and we've just multiplied everything by cos theta over cos theta, okay, because cos theta over cos theta is 1. And the way we've actually done it is we've multiplied it in a way that we have divided all the terms by cos. And so we've ended up with mv sine theta over this cos theta, right? We are actually dividing this one and also dividing this one. Right, we could have multiplied the 2 out and then refactorized it, but we can just logically work out that what's happening here is we're taking cos theta over cos theta plus sine theta over cos theta. This is going to become tan. This is going to become 1, and that's also going to become tan theta. That's finally going to give us mv squared tan theta all over 2 mu, because the cos theta has become 1, plus tan theta. And if we go back to the original statement, as required. Okay, so a fun little one where we've had to use all the tools that we've learned along the way in order to calculate the height, in order to calculate the increase in gravitational potential energy.